Before you drift off, imagine the universe has a file size. Tonight we calmly weigh arguments for and against simulation, with simple math you can follow half awake, and one quiet physics experiment waiting. If you want a calm track you can replay, tap like and save this video now. At 1 a.m., you can find it again without searching. Let's move slowly and define our words, because this topic gets confusing when the definitions slide. When people say simulation, they can mean several different ideas that overlap, but do not match. At the simplest level, a simulation is a set of rules that generates behavior that looks like something else. In science, we simulate weather, galaxies, and pandemics to learn patterns, not to replace reality. The hypothesis we're exploring tonight is stronger than that scientific use. It suggests the world you wake up in is not merely modeled, but actually produced by some computing process. That sounds dramatic, so we'll keep it gentle and precise. Think of simulation as a spectrum, not a single claim with one fixed shape. On one end is high fidelity everywhere, like a universe computed down to the smallest detail at all times. On the other end is selective fidelity, where only what matters for observations is computed in detail. If that reminds you of how video games render what the player can see, that is the common analogy. But we should treat it as an analogy, not a proof, and not a description of how reality must work. Selective fidelity can mean many things, and some versions are scientifically meaningless. It could mean coarse graining, where fine details are not stored because they do not affect anything measurable. Or it could mean hidden variables, where the detail exists but is inaccessible to us for principled reasons. So when someone says, "I think we live in a simulation," your first calm question is, which kind? A second distinction is about purpose, or at least the type of world being generated. One version is an ancestor simulation, a historical replay meant to model a past civilization in detail. In that picture, you and I might be like agents inside a reconstructed history, living through ordinary days. Another version is a physics engine universe, not a replay of history, but a world that simply follows rules. It could be designed for experiments, for art, for curiosity, or for reasons we cannot guess. And it could be designed for no purpose at all, like a byproduct of some larger system. A third distinction is easy to miss, and it matters for how we talk about evidence. Sometimes simulation just means model, like a toy universe that helps us understand ours. And sometimes simulation means world, meaning the toy universe is the only universe its inhabitants ever meet. So, tonight, when we say simulation hypothesis, we mean the world itself, not only a model on our desks. That brings up a word people often use, real, and it has more than one meaning. Real can mean the experiences feel vivid and consistent from the inside. And real can mean the underlying substrate is what we usually imagine, like particles in space and time. Those two can come apart without making your life meaningless. If you step on a sharp stone, the pain is real as an experience, even if the substrate were different. Joy can be real, learning can be real, and kindness can be real, because they are patterns in experience. A simulation claim changes the base layer story, but it does not automatically erase what happens within the layer. This is a calm point that many philosophers emphasize in different ways. If minds are defined by what they do, not by what they are made of, then experiences can be genuine on many substrates. That idea is often called substrate independence, but we will treat it as a working assumption, not a conclusion. It is a way to keep the conversation clear, not a way to win the argument. If you dislike substrate independence, you can hold that position too, and we will return to it later. For now, we can separate two questions that are often tangled. One question is, what is the world made of at the deepest level? The other question is, what kinds of minds and meanings can exist inside whatever that deepest level is? Even if you suspect the simulation idea is wrong, these distinctions help you think more steadily. Now let's also say what the hypothesis does not claim, because the internet loves the loudest version. It does not claim that everyday life is full of obvious glitches, like a movie with a broken special effect. Anecdotes about repeating numbers, strange coincidences, or feeling watched are not strong scientific evidence. Humans are pattern finders, especially when tired, stressed, or looking for comfort in a story. If you want science, you need observations that are public, repeatable, and connected to a clear prediction. The simulation idea also does not automatically imply a divine designer who deserves worship. A simulator could be a scientist, a hobbyist, a corporation, or something we cannot categorize. And even if there were a simulator, that alone would not tell us their motives, ethics, or competence. It also does not predict doom, punishment, or an approaching end-of-world deadline. Those are narrative add-ons that feel intense, and we're not doing intensity here. Another non-claim is that science stops working if the world is simulated. Science is about finding stable regularities in observation, and those regularities can exist in any well-behaved world. If the rules are consistent, you can still do physics, build bridges, and make reliable predictions. In fact, the more consistent the world is, the less useful the word glitch becomes. So, in a calm way, the simulation question is not, can we still do science? It is, what is the best explanation for why science works as well as it does? That takes us into philosophy of science, where humility is often a strength, not a weakness. There is a classic idea called underdetermination, which says different deep stories can fit the same data. Two theories can predict the same observations while disagreeing about what is really out there. In that case, evidence alone may not settle the metaphysical question, at least not quickly. That is not failure. It is just a reminder of what evidence can and cannot do. Another helpful contrast is between instrumental success and metaphysical certainty. Instrumental success means a theory helps you predict and control observations in a steady way. Metaphysical certainty means you are sure the theory describes the ultimate furniture of reality. Science often earns the first long before it earns the second, and sometimes never earns the second. This is one reason the simulation idea can feel both intriguing and slippery. It points at the deep layer, while most of our tools were built to study the patterns in our layer. So here is a relaxing frame you can keep in the background of your mind. Treat the simulation hypothesis as a form of epistemic humility, a way to remember we might be wrong about the base story. You can hold it lightly, like a smooth stone in your hand, without squeezing it into certainty. If your thoughts race at night, this can become a single track. Definitions, distinctions, and gentle limits. Notice how that already lowers the temperature of the question. We are not trying to scare ourselves with a hidden puppet master. We are practicing careful thinking about what it would mean for any claim to count as knowledge. Now, to keep your attention without rushing, I'll name a few open loops we will close later. First, there is the probability argument, often linked to philosopher Nick Bostrom, and it hides assumptions we should inspect. Second, there is the physics question, whether the universe allows the computation such a simulation might require. Third, there is the mind question, whether consciousness could exist inside a simulated world and what ethics follow. Fourth, there is the testing question, what an actual experiment could look like beyond stories and vibes. You do not need to memorize that list, because we will revisit it slowly as we go. For now, just let it sit there as a gentle promise that this will be structured and complete. So, to summarize this section in one calm breath, simulation can mean many things, and we must choose which meaning we are evaluating. And whatever the base layer is, your experiences can still matter, because meaning lives in patterns of living. With our definition steady, we can trace where this question comes from, long before computers existed. Before computers, before screens, people still wondered how firm reality really is. This is not a new fear, and it does not have to be a loud one. It is an old habit of careful minds, testing what you think you know. One gentle way to start is with dreams. In a dream, the world can feel complete, detailed, and emotionally real. Then you wake up, and the certainty dissolves without any warning. Long ago, the Chinese thinker Zhuangzi told a famous story about dreaming he was a butterfly. He woke and wondered, was he a man who dreamed a butterfly, or a butterfly dreaming a man? The point is not that dreams are evil or meaningless. The point is that experience alone does not label itself from the inside. Western philosophy developed similar puzzles in different words. The details differ, but the calm pressure is the same. How do you know you are not dreaming right now? Most of the time, we answer by habit, not by proof. We trust memory, consistency, and the way the world pushes back when we test it. But the dream argument shows a limit. Vividness is not a certificate of truth. It is an invitation to look for stronger standards than feeling. A later style of thought experiment sharpens the same concern. Imagine you are only a brain kept alive, receiving perfectly crafted signals. Everything you see and hear is fed in like a private theater. This is often called the brain in a vat scenario. It is not meant to be a prediction about real laboratories. It is meant to ask what knowledge would survive even under extreme deception. If all your evidence comes through experience, can experience verify its own source? Some philosophers say no, not completely. Others say we still have tools like logic, coherence, and the success of prediction. Either way, the question stays quiet and persistent. What makes a belief more than a story you happen to be inside? Now we arrive at one of the most influential voices of methodical doubt. In the 17th century, René Descartes tried to rebuild knowledge from the ground up. He decided to doubt anything that could be doubted, even ordinary perception. He imagined a deceiver powerful enough to trick him about everything. Sometimes this is described as an evil demon, but you can hear it as a pure thought experiment. The purpose was not to frighten, but to find one stable point. Descartes found that doubting still required a thinker doing the doubting. So even if the world were deceptive, the fact of conscious thought seemed undeniable. That famous move leads to the line, "I think, therefore I am." Whether you accept it or not, notice the shape of the project. It separates the inside fact of experience from the outside story about what produces it. That separation is exactly where modern simulation talk likes to live. And now we can shift, softly, into why computers revived these older questions. Computing gave us new metaphors that feel vivid and easy to picture. We can build small worlds with rules and watch complex behavior emerge. We can make convincing illusions and sometimes forget they are illusions. Virtual reality, spelled VR, made this especially intuitive. A headset can place you inside a space that reacts to you, even if it is generated. Games also offer a familiar image, worlds rendered by code with physics that is good enough. But metaphors are not evidence, and they can mislead when taken too literally. A game engine has goals, shortcuts, and visible limits that may not map to nature. Still, the metaphor can help us ask clearer questions. If a world is rule-governed, what kinds of rules could generate what we observe? This is where the phrase digital physics appears. Digital physics is not one doctrine, but a family of proposals. Some versions suggest space-time might be discrete, like a grid at an unimaginably tiny scale. Other versions suggest that information is the deepest currency, with matter as a kind of bookkeeping. A related idea is that physical laws might be understood as constraints on information processing. This is not automatically the same as saying, therefore we are simulated. It is more modest. Maybe the universe is describable in computational terms. In the 20th century, Claude Shannon formalized information in a way that influenced many fields. Separately, physicists like Rolf Landauer emphasized that information is physical, tied to energy and entropy. These ideas encouraged a certain style of thinking. Treat the world as something that computes. John Archibald Wheeler captured a mood with a phrase often repeated as it from bit. But again, a slogan is not a conclusion. It is a way of pointing at a research program, not a proof of a hidden computer. There are also cellular automaton ideas, where simple update rules can create rich patterns. They show how complexity can arise without a designer tweaking every detail. Yet even if a cellular automaton can resemble physics, resemblance is not identity. The lesson is possibility, not confirmation. So modern computing did not invent doubt, it refreshed it. It gave old puzzles a new costume that fits the imagination more snugly. Now let's add a calming layer from philosophy of science. Many working scientists are comfortable being agnostic about ultimate substance. They focus on what theories let us predict, measure, and control. This attitude is sometimes called instrumentalism, though real scientists vary widely. The key is practical humility. Do not demand metaphysical certainty as the price of doing good work. A related view is structural realism. Structural realism says we may grasp the structure of the world better than its inner nature. For example, we might know the relationships and equations that connect phenomena, but we might not know what the entities are like in themselves beyond those relations. This is attractive because science often preserves structure across revolutions. The math of patterns can survive even when the story about what exists changes. Model-based realism offers another soothing angle. On this view, theories are models that capture aspects of reality, not mirrors that show the whole thing. Models can be true enough in context, even if incomplete or idealized. Think of maps. A subway map is not a street map, yet it can be perfectly useful. In this light, simulation talk becomes less emotional. It becomes one more proposal about the deep story behind the structures we track. And it reminds us that multiple deep stories can fit the same reliable surface patterns. That is the undercurrent we will keep returning to tonight. Now, before we move on, let's do a gentle reset with 3 takeaways so far. First takeaway, the question is old. People have asked, am I dreaming? For as long as we have written records. Take a slow breath and let that settle. Second takeaway, the vocabulary is new. Computers, information, and VR give fresh images, but the basic doubt predates them. Take another slow breath and let that settle. Third takeaway, the emotional tone can be quiet. You can explore uncertainty without turning it into panic or turning it into a belief system. One more slow breath and let that settle. With that calm foundation, we are ready for the argument that made simulation talk feel like a formal problem. It takes late-night curiosity and turns it into a probability fork. Now we arrive at the argument that turned late-night curiosity into a formal probability problem. Bostrom's trilemma. Now we reach the argument that made the simulation idea feel like a neat, almost mathematical puzzle. It was written by philosopher Nick Bostrom, and it is often called a trilemma. A trilemma is a 3-way fork where at least one option must be true, even if none feels pleasant. We will walk through it slowly, like following a quiet path at night. First, we set the stage with one key idea. A sufficiently advanced civilization might run detailed simulations of people. Bostrom focuses on a special case he calls ancestor simulations. An ancestor simulation is a high-detail replay of a civilization's past, populated by conscious beings like us. History is a tempting target because it is rich with drama, data, and meaningful outcomes. A simulator might want to study how societies grow, collapse, cooperate, or invent. Or they might simply want to know what it felt like to live in earlier centuries. In this argument, the simulator is not necessarily divine, or even wise. They are just a civilization with very powerful technology and enough interest to use it. Bostrom uses a word that can sound loaded, posthuman. Here, posthuman does not mean morally better or spiritually elevated. It means a level of technological capacity far beyond what we have now. Think of it as engineering strength, not moral status. The argument also leans on a quiet unit of counting, observer moments. An observer moment is one slice of conscious experience at a time, like a single moment of being you. It is not your whole life, and it is not a whole person across decades. It is more like a single frame in the movie of experience. Why does that matter? Because when you count experiences, you must decide what exactly you are counting. Are you counting people? Are you counting lives? Or are you counting moments of awareness? Bostrom's framing tends to treat observer moments as the lottery tickets in the probability draw. That choice is subtle, and we will come back to it later as a hidden assumption. For now, keep it as a gentle placeholder. The argument is about how many experiences exist in total. Now, the trilemma itself is surprisingly short when stated plainly. It says that at least one of three statements is true. Statement 1. Almost all civilizations like ours go extinct before reaching that powerful post-human level. Statement 2. Even if some civilizations reach that level, almost none choose to run many ancestor simulations. Statement 3. Civilizations do run many such simulations, and in that case, we are very likely to be in one. Notice how calm that is. It is not claiming we are simulated as a fact. It is offering a conditional fork about what would follow if certain things are possible. Let's take the horns one by one, starting with the third, because it grabs attention. Horn 3 says they simulate a lot. If they simulate a lot, then simulated minds may vastly outnumber non-simulated minds. And if you assume you are a typical mind among minds like yours, then you should expect to be simulated. That is the basic intuitive punch. It sounds like a magic trick, but it is really a counting argument plus a typicality assumption. We will unpack both parts carefully. Now, Horn 2 says, some civilizations reach the capacity, but they do not simulate ancestors in large numbers. They might have ethical rules that forbid it. They might see it as cruelty, like creating suffering for entertainment. They might have laws, treaties, or cultural taboos against making conscious copies. They might also find it boring, or pointless, or socially shameful. Or they might have technical reasons that make it less appealing than it sounds. Horn 1 is the bleakest. Civilizations do not make it that far. They might self-destruct, or be destroyed by natural catastrophes, or quietly stagnate. They might never solve the energy problem, the stability problem, or the governance problem. Or they might solve those problems but then face something else they cannot predict. So the trilemma is a way of saying, either we tend to die out, or we tend to refrain, or we tend to simulate. And if we tend to simulate in huge numbers, we might be in the simulated majority. Now, to make this feel concrete, we will do a small toy calculation. This is not a proof, and it is not meant to be intimidating. It is meant to show why large numbers create the sensation of statistical pressure. Imagine first, one advanced civilization that chooses to run ancestor simulations. Suppose it runs just one simulation of a past society roughly like ours. Now imagine the simulation includes 1 million people over 1,000 years. That is a lot of lived experience, even with modest numbers. If you picture 1 million people living ordinary days for 1,000 years, the total number of life years is enormous. Now, suppose the civilization runs not one such simulation, but 1,000 simulations. 1,000 is large, but not absurd for an advanced society with vast resources. Now, our 1 million people becomes 1 billion simulated people across those simulations. And the 1,000 years of history becomes a mountain of observer moments. Already, the simulated population could outweigh the base population, depending on how you count. If there are only a few base civilizations and many simulated histories, the simulated minds dominate the pool. The typicality step then says, if you are drawn at random from that pool, you are probably in the larger part. That is the whole engine of the argument. A tiny shift in how many simulations exist can flip the conclusion from unlikely to likely. This is why people call it a probability fork. Now, let's slow down and do the same idea with smaller steps. Start with one civilization in base reality, meaning not simulated, just the original physical substrate. That civilization contains, say, 10 billion people over time across its full history. Now imagine it creates simulations of its ancestors. If it creates 10 simulations and each simulation contains 10 billion conscious people over time, that is 100 billion simulated people. In that case, simulated people are already 10 times more common than base people in that simplified count. If it creates 1,000 simulations, the ratio becomes 1,000 to 1. At that point, if you accept typicality, the prior probability starts to lean heavily toward being simulated. This is the intuitive picture people carry around, a multiplier effect. One world can create many worlds, and then most observers are in the copies. But toy numbers can hide as much as they reveal. So now we gently step into the assumptions that control the conclusion. Assumption 1 is about measure, meaning how you count conscious observers in the first place. Do you count each person as one ticket, no matter how long they live? Do you count each second of experience as a ticket, making longer lives carry more weight? Do you weight intense experiences more than calm ones? Or do you weight all moments equally? This matters because a simulator could create many short lives or a few very long ones. The result depends on the chosen measure, and there is no universally accepted answer. Some measures can create paradoxes, where adding observers changes probabilities in strange ways. This is one reason anthropic reasoning can feel slippery. Assumption 2 is the reference class, which is the set of observers you treat as comparable to you. Who counts as like you in the lottery? Is it all conscious beings in the cosmos? Is it only human-like minds? Is it only minds with your level of intelligence and memory? Is it only minds living in a world with these specific laws of physics? If you widen the reference class, you might include vast numbers of minds very unlike you. If you narrow it, you might exclude many simulations or include only a special subset. The conclusion can swing just by changing the boundary of who is included, and there is no obvious, non-arbitrary way to draw the boundary. Assumption 3 is substrate independence, the idea we introduced gently earlier. It says a mind could, in principle, exist on different physical substrates if the right functional patterns are present. If substrate independence is false, then ancestor simulations might be mere animations, not conscious worlds. In that case, the simulated minds do not count, and the probability pressure disappears. If substrate independence is partly true, but only under strict conditions, then the number of conscious simulations may be far smaller than imagined. So, a lot hinges on what you think consciousness requires. Another assumption hides in the phrase, they simulate a lot. What counts as a simulation of conscious beings? Does it require perfect detail down to every atom? Or can it be coarse, so long as it preserves the patterns that generate minds? A simulator might use shortcuts that keep minds intact while simplifying irrelevant physics. Or the shortcuts might break the very features that allow consciousness to arise. We do not yet know which direction is right, and this is another open loop we will close later. There is also an assumption about motivation. Why would a civilization spend resources to simulate ancestors? Maybe curiosity drives them and the simulations are treated like museums you can walk through. Maybe research drives them and they run controlled variations on history, like re-rolling key decisions. Maybe entertainment drives them, but that version often says more about us than about them. Or maybe they rarely do it at all, because the moral weight feels too heavy. This is where Horn 2 gains strength. Even with ability, choice can reduce the number of simulations to near zero. Now, let's talk about the strongest critiques in calm language. One major critique targets typicality arguments. Typicality is powerful because it feels fair to assume you are not special. But it is fragile because it depends on what you think the sampling process is. In real lotteries, you know how tickets are printed and how draws happen. In the observer lottery, you do not know the mechanism that selects which observer you are. Some philosophers argue that without a clear sampling story, typicality becomes a preference, not a fact. Another critique is that the argument is not evidence, it is conditional reasoning. It says if there are lots of ancestor simulations, then you are probably in one. But it does not show that there are lots of ancestor simulations. So it can feel persuasive while adding no new observational support. It is like saying, if there are many more fish than birds, then a random animal is likely a fish. That is true. But it does not tell you the fish-to-bird ratio in your actual world. A further critique points out that the conclusion can flip if any assumption weakens even slightly. If extinction is common, Horn 1 dominates. If ethics prevents simulation, Horn 2 dominates. If consciousness is not portable, Horn 3 collapses. If reference classes are unclear, the probability cannot be pinned down. So the argument is clean in form, but unstable in outcome. It is a well-built hinge attached to a door we are not sure exists. There is also a critique about what ancestor simulations would actually look like. If a civilization wants knowledge, it might simulate only simplified models, not full conscious populations. It might simulate economics, climate, or epidemiology without making everyone inside a real person. It might run agent models that are clever but not conscious. In that case, the total count of conscious simulated observer moments could be far smaller than the popular story suggests. And if the goal is entertainment, the civilization might prefer fictional worlds, not accurate pasts. So even granting advanced capability, the space of motives does not automatically produce a vast pile of ancestor lives. Another critique is a quiet one about humility. We are using our own social imagination to predict what alien or future minds would do. That is a weak kind of evidence, because it projects today's human instincts into unknown contexts. So Horn 2, the choice not to simulate Horn, remains hard to estimate. Now, let's return to the toy calculation and add one more gentle caution. A toy model multiplies simulations as if they are easy to run, like copying a file. But the cost might not scale that way. A full universe might be unimaginably expensive to compute in detail. If so, the number of conscious simulations could be small, even for a very advanced civilization. This is exactly why we need physics next. Because the most important question might not be philosophical at first, but practical. What does the universe allow any computer to do, no matter how advanced it becomes? Still, before we leave Bostrom, we can extract what is valuable in his argument. It forces us to be explicit about hidden assumptions. It shows how anthropic reasoning can create big shifts from small changes. And it gives us a structured way to talk about a topic that often becomes pure mood. If you are listening half asleep, you can keep one simple image, a three-way fork. Either civilizations usually end early, or they usually refrain, or they usually simulate many histories. If they do simulate many histories, then counting alone makes it plausible we are in one. But that plausibility is conditional, not a discovery. Now we can set up the next section with a calm promise. There is a surprising idea that can make simulations cheaper than you might expect. It involves focusing computation where it matters and compressing what does not. But even with clever shortcuts, physics imposes hard limits. Energy, entropy, speed, and information capacity set boundaries that no engineering can break. So the question becomes practical and grounded. Even if the logic of the trilemma is tidy, can any machine actually run a world like ours? So the next step is to leave pure probability for a moment and ask what the universe permits. So the question becomes practical. What does the universe allow a computer to do, no matter how advanced? Quick, sleep-friendly check-in. If you feel like it, leave a comment with just one number. Type 1 for extinction before post-human tech. Type 2 for reaching it, but choosing not to simulate. Type 3 for running many simulations so simulated lives dominate the count. No explanation needed. This is just a quiet vote, like placing a pebble on one side of the scale. Later, I will glance at the overall spread just to see where our intuitions land. All right. With your intuition logged, let's look at the hard physical budget: information, energy, and time. Now we take the simulation idea out of pure philosophy and place it under a quiet desk lamp. Physics. If a world is being computed, then information, energy, and time are the budget lines. And physics is not flexible about budgets. First, a grounding thought. Information is not abstract fluff. In modern physics, information behaves like a physical resource, tied to entropy and to what can be distinguished. If you can reliably store a difference, that difference has a physical footprint. This leads to a family of results called information bounds. They are not all agreed on in every detail, but the direction is clear. Finite regions have finite capacity. A famous clue comes from black holes. Black holes behave like thermodynamic objects, with temperatures and entropies. When physicists calculated that entropy, something surprising happened. The entropy seemed to scale with surface area, not volume. That observation helped inspire what is called the holographic principle. The holographic principle, in simple terms, suggests that the maximum information in a region may scale with its boundary area. It sounds like science fiction, so we keep it careful. It is a clue, not a settled description of everyday space. In some theories of quantum gravity, it has strong support, especially in special idealized settings. But many physicists treat it as suggestive rather than universally proven for our cosmos. Still, even as a hint, it changes how you picture storage. If surface area matters, then packing more space into a region does not automatically pack unlimited information. Another related idea is the Bekenstein bound. The Bekenstein bound is a limit on how much information can be contained in a finite region with finite energy. Again, think of it as an upper ceiling, not a claim that nature always sits right at the ceiling. The calm takeaway is simple. If you try to store a whole universe state, you do not get infinite room for free. If a simulator is storing the full microstate, it must store it somewhere physical. And the storage medium has limits, even in principle. This does not disprove simulation, but it reshapes the naive picture of effortless copying. You cannot just say, compute everything and wave away the cost. Now, a gentle question. Do you even need to store everything? Real physics often works by ignoring details that never matter for prediction. The next sections will lean on that idea, but we can already place a marker here. Information bounds push you toward compression, toward clever representation, and toward leaving some details unspecified. Now we move to the second budget line, energy and the quiet role of heat. If you have ever used a laptop on a blanket, you have felt the basic fact. Computation makes heat, and heat must go somewhere. For a small device, a fan is enough. For universe-scale computation, cooling becomes its own engineering universe. The key principle here comes from Rolf Landauer. Landauer's principle says that erasing information has a minimum energy cost. That cost shows up as heat dumped into the environment. The phrase to remember is gentle. Erasure is expensive. Not expensive in dollars, but expensive in unavoidable physics. You can compute in many ways, but if you routinely overwrite bits, you must pay in heat. A simulator that updates a world by constantly deleting and rewriting might face an enormous thermal bill. This is why discussions of computation limits often focus on entropy management. You can think of it as the cost of cleaning up after yourself. Now, there is a partial escape hatch, and it has a calm, elegant name: reversible computing. Reversible computing aims to perform operations without erasing information at each step. If you never erase, the Landauer cost can, in principle, be pushed very low. But reversible computing is not free magic. It tends to require careful designs, extra memory, and long chains of bookkeeping. And eventually, if you want to extract a definite answer and reset for the next run, some erasure usually returns. So reversible computing is best seen as a way to shift costs around, not to remove them entirely. It says you can trade time and space for less heat up to a point. This matters for simulation talk because it highlights a constraint most people forget. The bottleneck may not be raw speed, but waste heat and the ability to export entropy. Now we move to the third budget line: how fast computation can proceed. Even with infinite cleverness, physics still has speed limits. One obvious speed limit is the speed of light. If your computer is spread across space, signals between parts take time. That delay is like latency in a network, but written into causality itself. This matters because a big simulation is likely distributed. You do not build a universe computer as one tiny chip. You spread it out to access energy and materials. But spreading out makes coordination slower. If different regions must agree on shared states, they must exchange information. And that takes time. You can design around this by letting regions evolve mostly locally. But then you face consistency constraints at the boundaries. In calm terms, distributed computing creates bookkeeping costs that scale with size. There is also a deeper limit that connects energy to maximum operation rate. Physicists have derived bounds where available energy sets an upper limit on how many distinct operations can occur per time. One well-known example is the Margulis-Levitin bound. In very simple language, it says energy is tied to how quickly a system can move between distinguishable states. Again, treat this as an upper bound, not a typical operating point. Nature often runs far below its theoretical maxima, depending on conditions. But for a simulator trying to push extreme throughput, upper bounds are exactly what matter. So, even a post-human computer has a ceiling. It cannot compute arbitrarily fast using finite energy. And if it tries to go fast, energy density and heat problems get worse. Now pause for one steady conclusion from these three lines of thought. Storage is limited, erasure costs heat, and speed is bounded by causality and energy. These are not opinions. They are the shape of the physics as we currently understand it. Does that kill the simulation hypothesis? Not necessarily. But it pushes the hypothesis away from a cartoon and toward an engineering problem. And once it is an engineering problem, you can ask sharper questions. For example, what would be the cheapest kind of simulation that still produces beings like us? That question leads to a calm, myth-busting step about precision. Many people imagine that simulating a universe requires perfect detail of every particle, forever. But physics itself suggests that perfect detail is not always necessary for stable experiences. In statistical mechanics, countless microstates look identical at human scales. The air in your room has a vast number of microscopic configurations that all feel like the same warm air. When you measure temperature, you do not track each molecule. You track a coarse variable. This is called coarse graining. Coarse graining is not cheating. It is how useful descriptions are built. A simulator that cares about producing consistent experiences may aim for coarse truth, not micro-truth. That phrase, consistent experience, is important. It means the world behaves in a stable way when you test it, learn from it, and share observations with others. A simulation that achieves that can feel fully real from the inside, even if it leaves some micro details implicit. Now, what about chaos? The idea that tiny differences explode into big outcomes. Chaos is real in many systems, like weather and turbulence. But chaos does not automatically mean you need infinite precision to have a coherent world. It means prediction can become difficult beyond some horizon, given limited knowledge. A simulator could accept that, because we accept it too. Our weather forecasts are useful without being perfect. More importantly, many chaotic systems have statistical regularities that do not depend on microscopic detail. So you can simulate the distribution and still get realistic behavior, even if you do not track every atom exactly. This is another way nature itself gives permission for compression. However, we should also be honest about the other side. If you want to replay exact history, down to each detail, you may need far more precision and storage. So the cost depends on the goal. An ancestor simulation that must reproduce a specific past would be expensive. A physics engine universe that only needs to be consistent could be cheaper. This difference matters for Bostrom-style arguments because it affects how many simulations are plausible. Now we arrive at the biggest shortcut people discuss: simulate what is observed. This is where the rendering analogy enters, and we will label it as an analogy. In computer graphics, you render detail where it will be seen and simplify where it will not. In a world with observers, the thought is that high detail might be allocated where measurements occur, and lower detail might be used elsewhere, as long as it never leaks into observable contradictions. This idea feels natural to many people because it matches how we manage limited resources in our own computers. But we have to keep the caution sign up. Nature is not a video game, and observation in physics does not necessarily mean a human looking. Also, a simulator cannot simply guess what will be observed without predicting observers, which is part of the same hard problem. Still, as a cost-saving picture, selective fidelity is worth considering. It is one reason simulation arguments sometimes feel less impossible than they first appear. If you do not compute every detail everywhere, the required resources can drop dramatically. Yet even selective fidelity has constraints. The world contains many interacting processes, and simplifications must preserve the right causal structure. If you simplify too much, anomalies appear, and science would likely discover them as persistent irregularities. So a successful selective fidelity simulation would need careful design, not casual shortcuts. Now, notice the interesting twist. Modern physics already contains places where what is definite seems to depend on measurement context. That does not prove simulation, but it makes the rendering metaphor feel less outlandish to some listeners. We will explore that carefully in the quantum section without rushing or sensational language. For now, we keep our promise: real numbers, real limits, calm implications. Let's tie the pieces together with a practical mental image. Imagine trying to run a vast computation inside a finite universe. You need memory to store state, energy to update it, and a way to dispose of heat. You also need time for signals to propagate so distant parts remain consistent. Every one of those needs a physical carrier: matter, fields, radiation, something. So, if our universe is computed, the computer itself must be part of some larger physical world. And that larger world must have its own laws and limits, which raises a simple question you can hold gently. Is it likely that the larger world offers vastly more resources than ours? It could, but we do not know. And if it does not, the number of high-fidelity simulations might be far smaller than the popular story suggests. Now, a calm skeptical note about holography and bounds. Some physicists argue that applying holographic ideas too literally can be misleading. A bound may tell you the maximum information needed to describe a region, not the actual information present. And the mapping between boundary descriptions and bulk reality is subtle and theory-dependent. So we should not treat surface area scaling as a direct statement that space is a pixel grid. It is a clue from a certain corner of theoretical physics, not a settled everyday fact. But even if holography is not universal, the general lesson remains. Physics limits information. And if information is limited, computation is limited. Now, another skeptical note about computation limits. Bounds like Margulis-Levitin describe idealized maximum rates under certain assumptions. Real devices face additional constraints: error correction, noise, material strength, and stability. When you compute near the edge, small errors can cascade, and then you must spend resources correcting them. So, in practice, the usable speed can be far below the theoretical cap. This again nudges the simulation idea towards selective strategies, not brute force. Now we can do a short, gentle recap to keep sleepy listeners oriented. First, Finite regions do not hold infinite information. Second, erasing bits produces heat, so cooling and entropy export are central. Third, computation across space faces latency and energy ties to maximum operation rate. Fourth, perfect microscopic detail is not always needed for stable macroscopic experience. And fifth, selective fidelity is a tempting shortcut, but only as an analogy, not as evidence. If you remember only one line from this section, let it be this: any simulation story has to pay the physics bill somewhere. Now we turn that bill into an open loop that points directly to quantum mechanics. If selective fidelity is possible, it would show up where the world becomes definite only when measured. Quantum theory is exactly where our everyday intuition starts to wobble. Some interpretations make observation feel oddly central, even if you remove human minds from the picture. And that is why a quiet physics experiment keeps appearing in serious discussions. We are not claiming it proves simulation. We are saying it is one of the clean places where the question becomes sharp enough to test carefully. So, with our budgets and limits in view, we can step into the strangest part of modern physics. And that brings us to the part where observation seems to matter more than intuition would like. Now we arrive at quantum mechanics, where our usual pictures of reality get very quiet and very strange. Not strange like a jump scare, but strange like a rule that refuses to fit in your hand. This is also where the word observation starts to sound important, and people reach for the renderer metaphor. We will use that metaphor carefully, like a flashlight, not like a conclusion. Quantum mechanics is, first of all, a toolbox for predicting outcomes of experiments. It tells you what you will likely see when you prepare a system and then measure it. What it does not clearly tell you is what the system is doing in between. That gap is often called the measurement problem. The measurement problem is not a single puzzle, but a family of puzzles. The calm version is, the equations give smooth evolution, but measurements give definite results. So, how do definite results arise from a theory that allows many possibilities at once? To stay grounded, let's define two words in an operational way. Superposition means the theory assigns more than one possible outcome to the same preparation. Measurement means you choose a procedure that forces a single outcome to be recorded. In the lab, this is not mystical. It is switches, lasers, detectors, and a readout that clicks or does not click. Quantum theory lets you compute probabilities for those clicks with extraordinary accuracy. So the debate is not about whether the math works. The debate is about what story, if any, we should tell about what is real underneath. Those stories are called interpretations. Interpretations make different claims about what exists, but they often agree on predictions in ordinary settings. This is why the simulation story can shift depending on which interpretation you lean toward. If the world is computed, does it compute one outcome or all outcomes? Does it use hidden variables or genuine randomness or something else entirely? We will take a slow carousel through a few well-known interpretations. We do not need to pick a winner tonight. We only need to see how each one changes the shape of the simulation conversation. First is the many worlds family of interpretations. Many worlds says the wave function never truly collapses. Instead, the universe evolves smoothly, and what you call a result is a branching of histories. You see one branch because you are inside one branch. In many worlds, randomness is more like self-location uncertainty. You are uncertain about which branch you will find yourself in after the interaction. For simulation talk, many worlds can feel expensive. If all branches are real, then the computation is not selecting one path, it is maintaining a vast structure of paths. Some people think a simulator would avoid that cost. Others think the simulator might exploit it if the underlying hardware is quantum and branching is natural. Second is the Bohmian family, sometimes called pilot wave theory. Bohmian mechanics keeps a definite configuration, like particle positions, at all times. The wave function still exists, but it guides the particles in a precise way. In this picture, there is no fundamental randomness in the underlying motion. The randomness comes from ignorance of exact initial conditions. For simulation talk, Bohmian mechanics can feel like a classical engine with an extra guiding field. But it also requires non-local connections, meaning distant parts of the system can be linked in a way that ignores simple distance intuition. A simulator could implement non-local rules easily if it is not bound by our space-time. Or non-locality could be a clue that our space-time story is not the deepest one. Third is the objective collapse family. Objective collapse says the wave function sometimes collapses as a real physical process. The collapse is not only about observers or measurements. It happens spontaneously or when systems get large or complex enough, depending on the model. In this picture, randomness is fundamental because the collapses are genuinely unpredictable. For simulation talk, objective collapse can resemble a built-in rule that forces definiteness. It can also resemble a cost-saving feature if maintaining large superpositions is difficult. But collapse models come with parameters, and physicists look for experimental signatures that would distinguish them. Fourth is cubism, spelled cubism. Cubism treats the wave function as a tool for an agent's expectations, not as a physical object out in the world. The probabilities are about what an agent should expect to experience when they interact with a system. This can feel relieving because it avoids the urge to picture a hidden movie running behind the scenes. For simulation talk, cubism can shift the conversation away from what is rendered and toward what is knowable. But it also makes some people uneasy because it sounds like reality depends on the agent in a strong way. Most cubism proponents do not say the world is made by your mind. They say the quantum state is a personal bookkeeping device for rational expectation. So already, you can see why interpretation matters. One interpretation makes outcomes branch, another keeps hidden variables, another adds real collapse, another reframes the wave function as belief. Yet, in practice, they often fit the same laboratory data in the ranges we have tested. Calm reset. Quantum mechanics is not one tidy story. It is a reliable calculator with multiple possible metaphysical readings. Now we turn to a key set of experiments that constrain the space of possible stories. These are Bell tests, named after physicist John Bell. Bell's theorem shows that no theory with only local hidden variables can match all quantum predictions. Local means influences do not travel faster than light. Hidden variables means the outcomes are fixed in advance by unseen properties. Bell showed that if you insist on both, you get limits called Bell inequalities. Quantum mechanics predicts violations of those inequalities in entangled systems. Experiments have repeatedly observed those violations in careful ways. The modern message, stated gently, is that reality is not both local and predetermined in the simple way many people hoped. Something has to give: locality, realism, or some other background assumption. This matters for simulation talk because it narrows your menu of underlying engines. If the simulator is using hidden variables, it likely needs non-local coordination. If the simulator wants strict locality, it may need branching or genuine randomness or another move. And if the simulator wants determinism, it must accept some form of non-local structure or a very different notion of what counts as real. Now let's talk about randomness, because people often say a simulation would use pseudo-random numbers. In everyday computing, pseudo-random means generated by a rule that looks random, but is fully determined. If you know the seed and the algorithm, you can reproduce every outcome. True randomness, in contrast, means no hidden rule fixes the outcome in advance, even in principle. Quantum physics is often presented as giving true randomness, but the meaning of true depends on interpretation. In many worlds, the full evolution is deterministic, but your experienced outcome is uncertain from your inside perspective. In Bohmian mechanics, the hidden variables are deterministic, but unpredictable, because you cannot know the exact initial state. In objective collapse, the randomness is built into nature as an irreducible feature. So when we ask, is quantum randomness real? We are asking a deep question with multiple defensible answers. Still, Bell tests give us something solid. They suggest that if outcomes are fixed in advance, the fixing cannot be local in the simple sense. So, either the world has non-local links, or it has indeterminism, or it has a branching structure, or it has an even stranger option. Now, there is a modern twist that sounds technical but can be stated simply. Some experiments can certify randomness without trusting the details of the devices you used. This is called device-independent randomness. The idea is, if you observe strong enough Bell inequality violations, then no local hidden variable strategy could have produced your data. Under standard assumptions like no faster than light signaling between the measurement choices, you can bound how predictable the outcomes could have been. So, you can extract bits that are provably unpredictable to any classical adversary constrained by those assumptions. This does not prove metaphysical free will. It proves a kind of operational unpredictability that is stronger than ordinary noise. For the simulation idea, this is interesting in two different directions. One direction says, if the world is simulated, it might still include certified randomness because the simulator chooses to include it. Another direction says, if a simulator wants determinism, it must hide it behind correlations that look like certified randomness to us. So, certified randomness does not rule out simulation, but it raises the bar for simplistic stories. It pushes you away from, the simulator is just rolling a cheap dice in the background. Now we turn to quantum computation and what it implies about simulating physics. A quantum computer is a device that uses quantum states to process information. The important point is not speed in general, but efficiency for certain tasks. Quantum systems can represent and evolve complex superpositions in a way that is natural for them. This is why physicist Richard Feynman suggested that simulating quantum physics might require quantum hardware. A classical computer can simulate quantum systems, but the resources can grow very fast with system size. That does not mean it is impossible in principle. It means it can become impractical if you demand full state tracking for large systems. So if our world is deeply quantum, a simulator might benefit from being quantum-like as well. In that case, the simulator is not a laptop running the universe. It is a universe-level quantum machine, or something even stranger, running a quantum-like process. But quantum computing comes with its own quiet difficulties. Quantum states are delicate, and they tend to decohere when they interact with the environment. Decoherence means the system loses the ability to show interference between alternatives. To do long computations, you need error correction. Error correction means spreading information across many physical components so local noise does not ruin the logical state. This often requires a large overhead in hardware and careful control. So quantum advantage is real, but it is not effortless. If a simulator is using quantum resources, it still pays in complexity, stability, and engineering constraints. Now we ask a simple question that many sleepy listeners appreciate. If the quantum world is so weird, why does your day feel so classical? Why does a table feel solid? And why do outcomes look definite almost all the time? A major part of the answer is decoherence. When a quantum system becomes entangled with its environment, the different alternatives stop interfering in practice. The environment acts like an information sink that spreads phase relationships into countless degrees of freedom. The result is that, for all practical purposes, the system behaves as if it has selected a classical outcome. Decoherence does not, by itself, pick one outcome as the only real one. It explains why the alternatives stop talking to each other and stop producing visible interference. So it builds a bridge from quantum math to classical experience. This bridge is part of why quantum mechanics can look like a renderer metaphor at first glance. You see definite results where interactions have effectively forced the world into stable records. But we should be careful again. Decoherence is a physical process, not a software trick. It does not imply a conscious observer is required. It implies that interactions that create durable records change what can be observed later. Calm reset. The simulation hypothesis does not depend on any single interpretation of quantum mechanics. You can imagine a simulated world with many worlds dynamics, or with hidden variables, or with objective collapse. The simulation question is about substrate and implementation, not about choosing a favorite metaphysical story. Still, quantum mechanics is relevant because it shows that the world already has deep constraints that look unlike everyday intuition. If a simulator uses shortcuts, quantum theory is a natural place to look for artifacts. Not artifacts like flickers or pop-in textures. Artifacts like subtle constraints on correlations, on information flow, and on what can be known at once. For example, quantum theory limits how much information can be copied perfectly, a feature called the no-cloning theorem. It also restricts how measurement outcomes can be jointly sharp, as in uncertainty relations. These are not bugs. They are stable structural rules. If the world is computed, such rules might be part of the compression strategy. They could be the price paid to keep the world consistent without storing every detail explicitly. Or they could simply be the way any consistent quantum-like world must behave, simulated or not. Now we prepare an open loop that will carry into the next section. People often claim they have found evidence of simulation in grids, noise, and patterns in physical data. Some of those claims are based on misunderstandings of quantum mechanics. Some are based on real physics, but stretched into a story it does not support. And a few point toward interesting, serious questions about discreteness and limits that physicists genuinely study. So our promise is to separate serious physics from internet folklore without mocking either side. We will ask what kinds of evidence would even count and what would not. And we will keep the tone quiet, because careful thinking does not need adrenaline. Here is the practical takeaway you can keep in your pocket. Quantum mechanics teaches us that the world can be consistent and measurable even when our mental pictures fail. It teaches us that deep reality may be described by constraints and probabilities rather than by tiny classical objects with fixed properties. That alone can make the renderer metaphor feel emotionally plausible to some people. But plausibility is not proof. The responsible move is to treat quantum weirdness as a place where tests are clean, not as a place where conclusions are easy. So if there were any clues at all, they would likely look subtle, like tiny constraints in the data rather than cinematic surprises. When people ask for evidence of simulation, they often picture something cinematic. A visible seam in the sky, a skipped frame, a flashing grid. But science usually works in the opposite direction. The strongest clues are quiet, statistical, and easy to misunderstand. So in this section, we will separate three things. First, ideas that are testable in principle. Second, ideas that are interesting metaphors. And third, stories that feel meaningful, but do not count as physics data. Let's start with the most common testable idea, discreteness. Discreteness means space or time might come in tiny indivisible steps, rather than being perfectly smooth. People call this pixelation, but that word can be misleading. A physical lattice is not the same thing as squares on a screen. If space-time had a grain, the grain would be unimaginably small, and its effects would be subtle. Here is the first guardrail any such idea has to respect. Lorentz invariance. Lorentz invariance is the principle that the laws of physics look the same for observers moving at constant speeds relative to each other. It is part of the structure of relativity, and it has been tested extremely well. A naive grid in space would tend to pick out a preferred direction or preferred rest frame. And that would usually show up as tiny differences in how particles behave depending on their direction of motion. So any discretization story has to answer a calm question. How do you have a grain without giving the universe a detectable set of favored directions? Some approaches try to build discreteness in a way that keeps Lorentz invariance effectively intact. Others accept small violations and then face experimental limits. This is where simulation discussions become more scientific and less story-like, because now you can ask what signatures would appear and whether we see them. So, what would a lattice-like spacetime do, in principle? One possibility is direction-dependent effects at very high energies. Particles moving along different directions could experience slightly different effective speeds or interactions. Another possibility is modified dispersion, meaning the relationship between energy and speed might change at extreme energies. If that happened, photons of different energies from distant events might arrive at slightly different times, or very energetic particles might lose energy in ways they should not, depending on the underlying rules. These are not easy measurements, but they are the kinds of things scientists actually look for. High-energy cosmic rays are one natural arena for this. Cosmic rays are particles, often protons or nuclei, that arrive from space with staggering energies. They have traveled long distances, and that makes them sensitive probes of tiny cumulative effects. If space-time had certain kinds of grain, the highest energy cosmic rays might show anomalies. For example, their arrival directions might reveal a subtle pattern, or their energy spectrum might shift in unexpected ways. Astronomy also offers other probes, like very distant flashes where timing can be measured carefully. The reason distance matters is gentle and simple. A tiny effect per kilometer can add up over billions of kilometers. Now, a calm caution. When you hear claims like, "Scientists looked for a grid," it is easy to imagine a single clear test. In reality, there are many models of discreteness and many ways they might hide their footprints. Some models preserve symmetries in clever ways. Some models place the grain in an abstract quantity, not in ordinary space. And some models predict effects far below what we can measure today. So tests can rule out families of models, but they rarely end the conversation with one dramatic verdict. This leads to a key point about evidence in simulation talk. A claim can always retreat to, "It is simulated better." If you do not see the artifact, you can say the simulator avoided that artifact. That means many versions of the hypothesis are hard to falsify in the strict sense. But that does not mean experiments are pointless. Null results still teach us, because they shrink the space of viable models. A null result means within the sensitivity of the test, we saw no deviation from the standard theory. It is not nothing. It is a boundary line drawn in the dark saying, not here and not this big. And over time, many null results can make whole classes of ideas very unlikely. This is one reason science feels slower than movies. Movies want one scene that resolves the plot. Science often works by narrowing. You rarely get a single door slam of certainty. You get a hallway of smaller and smaller doors. Now let's spend a moment on what it means when experiments find no deviation. It means the standard model of particle physics and relativity continue to predict observations with remarkable accuracy. It means if there is new structure, it either hides very well or lives at scales we cannot yet touch. And it means any simulation story that relies on coarse shortcuts must respect how precise the world appears. If you claim the simulator is cutting corners, you must explain why we keep failing to detect the seams. So precision is not an enemy of wonder. Precision is a constraint that keeps wonder honest. Now we come to a specific line of evidence claims that sounds almost tailor-made for simulation talk. This is the idea of holographic noise. It is connected loosely to the holographic principle we mentioned earlier. If space-time information is limited in a way tied to surfaces, some people wondered if there could be a fundamental kind of positional fuzz. Not fuzz from ordinary vibration or thermal noise. A deeper, irreducible noise that comes from space-time itself. If that kind of noise existed, it might show up in exquisitely sensitive instruments called interferometers. An interferometer uses light paths to measure tiny differences in distance. It is an instrument built to notice extremely small changes, so it became a natural place to look for any grain-like signature in space. One experiment that often comes up in serious discussions is the holometer. The holometer was built to test for a specific kind of correlated noise that some holographic ideas suggested. Correlated is the key word. If the noise is fundamental, two nearby instruments might share a faint pattern in their fluctuations. Ordinary noise is usually uncorrelated, each instrument rattling in its own way. So the idea was to build two interferometers side by side and listen for a shared whisper. It is a quiet experiment in the literal sense. It listens, patiently, for a pattern you would never notice by eye. And it is a good example of how simulation-adjacent ideas can be brought into contact with measurement. Now, how should we interpret results from something like the holometer? With restraint. A specific model predicts a specific signature. If the signature is not found, that model is constrained or ruled out, at least in that form. But the broader philosophical idea, space-time might be informational, is not automatically defeated. It means one proposed way that idea could manifest did not show up in that test. This is why internet summaries can be misleading. They might say holographic noise was disproved or simulation was disproved. What is really happening is more surgical. One kind of predicted correlated noise was not seen at the expected level. That is still valuable because it closes a door that was previously open. It also teaches a softer lesson. Even when a question sounds metaphysical, the best versions of it try to make contact with real instruments. Now, let's step back and talk about the phrase code-like structure. People often look at physics and say it looks like code. They point to elegant equations, quantization, conservation laws, and symmetries. They point to the way complex behavior arises from simple rules. But looking like code is not the same as being code. It can be a category mistake to move from metaphor to mechanism without evidence. Scientists use metaphors all the time because metaphors help intuition. But scientists also try to label metaphors as metaphors, so the metaphor does not start doing the work of proof. A helpful example comes from modern theoretical physics and holography. In some versions of holography, especially the ADS-CFT correspondence, space-time geometry is related to quantum information in a boundary theory. Researchers noticed that aspects of this relationship resemble quantum error-correcting codes. Error correction in computing is a way to protect information against noise by spreading it across many physical pieces. In holography, certain bulk features appear robust even when parts of the boundary data are disturbed. That robustness has a code-like flavor. It is beautiful mathematics, and it is a real research program. But it does not mean the universe is literally a computer program with lines of code written somewhere. It means certain structures in physics can be modeled with tools that are also useful in information theory. The metaphor points at deep connections, not at a literal file you could open. So when you hear the universe uses error-correcting codes, the calm translation is this: some equations of quantum gravity behave in ways that resemble information protection. That is interesting, but it is not direct evidence of an external simulator. Now, another common evidence claim is fine-tuning. Fine-tuning means the constants of physics seem to sit in a narrow range that allows complex chemistry, stable stars, and long-lived structure. If the constants were very different, the story goes life like us might not appear. This observation motivates several different explanations. One is that there are many universes with different constants, and we find ourselves in one that permits observers. That is an anthropic selection story. Another is that there is some deeper theory that forces the constants to be what they are, and they only look chosen because we do not yet see the deeper constraint. Another is that some kind of design or selection occurred. Simulation can be one form of that, where a simulator chooses parameters for a world of interest. But notice something important. Fine-tuning is not a measurement of a simulator. It is a prompt to ask why the parameter space looks hospitable, and multiple explanations can multiply faster than the evidence that discriminates between them. This is where philosophy of science becomes practical. A good explanation does not only fit what you already know, it also makes new risky predictions or connects to independent lines of evidence. Many fine-tuning stories struggle with that second part. They can fit the same observation by adding different deep narratives. So we should treat fine-tuning as an invitation to humility, not as a proof stamp. Now, let's touch a related issue: the temptation to overread patterns. When people are tired, stressed, or searching for meaning, pattern detection turns up. This is normal human cognition, not a personal flaw. Your brain is tuned to notice signals because in nature, missing a signal can be costly. But that same talent produces false positives. You can find faces in clouds, messages in static, and destiny in coincidence. Psychologists sometimes call this apophenia, the tendency to perceive meaningful patterns in randomness. There is also confirmation bias, where we notice supportive details and forget the rest. And there is the clustering illusion, where random events naturally form clusters that look suspicious. These are not insults. They are reminders of how inference hygiene works. So how should we treat glitch stories? Treat them as psychology data, not physics data. A story about a strange coincidence might tell you about memory, attention, stress, or perception. It does not tell you about Lorentz invariance, interferometers, or cosmic rays. If you want physics evidence, you need a measurement protocol, not a personal anecdote. This is also why science can feel emotionally calming when done well. It gives you a slower tempo. It asks you to step back from the urgent story and look for stable, shareable patterns. Now, let's connect these themes with a gentle contrast. Movies love a single artifact like a visible grid that proves the twist. Science, instead, tends to look for tiny deviations from a well-tested baseline. It looks for direction-dependent effects, correlated noise, timing shifts, and statistical signatures. And when it finds none, it does not shrug. It updates the map of what kinds of worlds remain plausible. This is the careful way to think about simulation evidence. Not, did we find the glitch? But, what model would imply what measurement, and did the measurement match? Now, to keep you oriented, here is a quiet checklist you can reuse anytime you hear a new claim. First, ask, is the claim precise enough to be wrong? Second, ask, does it predict a new pattern, not just reinterpret an old one? Third, ask, is there an experiment or observation that could, in practice, check it? And fourth, ask, does the claim survive contact with null results and known constraints? If it fails at the first step, it is probably a story, not a scientific hypothesis. Stories can still be meaningful, but they belong in a different drawer. Now we can return briefly to the lattice idea with this checklist in mind. A lattice like spacetime is, in some versions, a precise enough claim to be wrong. It risks breaking Lorentz invariance, and that is testable. So people test it, and many simple versions are strongly constrained. But other versions rebuild symmetry in subtle ways or push effects below current reach. So we do not get a clean yes or no. We get an evolving boundary of plausibility. That is the normal shape of science. Now we return to holographic noise with the same attitude. It was a specific claim about correlated fluctuations that could be measured. It was tested with sensitive interferometers. The non-detection tells us that particular signature is not present at that scale and sensitivity. That is how a serious conversation stays serious. It is not about winning a debate. It is about trimming away what does not match the world. Now we revisit the renderer metaphor one last time, carefully. If a simulator used shortcuts, we might expect artifacts at the edge of what is observed. But the edge of what is observed is not only human attention. It includes every physical interaction that leaves a record, including in distant stars and detectors. So hiding artifacts is harder than it sounds. A simulation that is consistent with precision physics might have to be, in effect, extraordinarily faithful, which circles back to the earlier point. If the simulation is always simulated better, then the claim slides away from testability. This is not a refutation, but it is a limit on what science can certify. Science can constrain models. it cannot always settle the deepest metaphysical label for the same model. So the responsible stance is a balanced one. Take proposed tests seriously, but do not overread them. Respect null results as real information. And treat personal glitch stories as human stories, not as laboratory reports. Now, a gentle reset to end this section. Discreteness is a testable idea, but it must respect strong symmetries like Lorentz invariance. Precision experiments and null results quietly box in many simple simulation-flavored models. Interferometer searches like the holometer show how a poetic idea can become a measurable question, and metaphors like code can inspire math without counting as evidence. With that hygiene in place, we can move toward a more personal question. If evidence is subtle and contested, the next question becomes personal and surprisingly ethical. What counts as a mind? One small, creative pause. If you could run one gentle test for a simulated universe, what would it be? Just one sentence in the comments. It can be a physics idea, a psychology idea, or a philosophy idea, as long as it is calm and clear. No pressure to be original. Sometimes the simplest tests are the most interesting. In a future video, I will read a few of the calmest ideas and sort them by what they would actually measure. All right. Now, let's slow down and talk about the part that matters most: consciousness, and whether a simulated mind can truly feel. We have talked about physics and probability, but the heart of the question is quieter. If the world were simulated, could a mind inside it truly feel? To approach that, we need one central idea and one central caution. The idea is called substrate independence. It means a mind might depend on pattern and organization, not on the specific material it is made of. The caution is that this idea is debated, not settled. Some thinkers find substrate independence obvious. Others find it deeply doubtful or even incoherent. So we will treat it like a hypothesis we can examine, not a banner we must wave. Let's start with a simple, gentle version of functionalism. Functionalism says mental states are defined by what they do in a system. Pain is the state that tends to cause avoidance, learning, and a certain kind of internal alarm. Joy is the state that tends to broaden action, reinforce behavior, and color memory in a stable way. On this view, what matters is the causal role, not the chemical recipe. If the causal roles are preserved, the mind is preserved. That is the claim, stated plainly. Now, why might someone accept it? Because we already see that many different physical systems can implement the same abstract computation. A melody can be played on a piano, a violin, or a gentle synth, and still be the same melody. A calculation can be done with beads, paper, or silicon, and still be the same calculation. So the functionalist asks, why would minds be different? But the skeptic asks a quiet counter-question. Is a mind more like a melody or more like a specific kind of flame? A flame has a pattern, but it also depends on its material conditions in a tight way. If you change the fuel and temperature, you can lose the flame entirely. So the debate is not silly. It is a real uncertainty about what consciousness depends on. A classic thought experiment makes this vivid without being harsh. Imagine a gradual replacement of neurons, one by one, with artificial components. Each replacement preserves the same input and output behavior. Each replacement fits into the network with the same timing and connectivity. At first, you would likely feel no change. After many replacements, you might still report feeling like yourself. At the end, if every neuron is replaced, are you still you? Functionalists tend to say yes because the organization is preserved. Skeptics tend to say no because something essential was lost along the way. But notice the difficulty. If the replacement is gradual and behavior remains the same, when would the mind disappear? Would it fade slowly or vanish at a particular neuron? And if it vanishes, would you notice it from the inside? This is where the thought experiment becomes a mirror for our intuitions. It tests whether you think consciousness has a sharp material boundary, or whether you think it rides on stable causal patterns. Now consider a related distinction that matters for simulation: emulation versus imitation. An emulation aims to reproduce the same internal causal structure, step by step, at the relevant level. An imitation aims to produce similar outward behavior without matching the inner structure. A chatbot that convinces you might be an imitation. A detailed brain simulation in principle would aim to be an emulation. If consciousness requires the right internal organization, imitation may not be enough. So when people say minds in code, the responsible question is, code that does what exactly? What level of detail is preserved? Neurons are not just on and off switches. They have timing, chemical modulation, plasticity, and rich interactions. But you do not necessarily need every micro detail to preserve function. Biology often tolerates variability while preserving behavior. So the implementability question becomes practical. Which features are essential for consciousness, and which are replaceable scaffolding? This is where neuroscience can help, even if it cannot settle everything. Neuroscience gives us theories about what consciousness is for and how it might be organized. One influential family of ideas is called global workspace theory. Global workspace theory suggests that many unconscious processes compete and cooperate. When something becomes conscious, it is broadcast widely across the brain, like a message sent to many systems at once. That broadcast allows coordination, planning, reporting, and flexible control. If that picture is roughly right, consciousness is not a single tiny spark. It is an integration event, a global availability of information. And integration events sound, at least in principle, implementable in different substrates. You could imagine a non-biological system with many specialist modules and a shared workspace. You could imagine attention-like routing and wide broadcast as a computational architecture. This does not prove consciousness is computation, but it shows how a consciousness-shaped function might be built. Another modern view is predictive processing. Predictive processing treats brains as machines that continually predict incoming signals. They compress the world by modeling what is likely, then updating when surprised. On this view, perception is not a passive camera. It is an active best guess, constantly refined by error signals. If that is roughly right, then minds are deeply tied to compression and prediction. And again, compression and prediction are not uniquely biological. Many systems can build models, minimize error, and stabilize behavior. So predictive processing can make substrate independence feel more plausible to some listeners. It suggests the core work of mind is an information task, not a tissue task. Still, we must stay balanced. A theory can describe what consciousness does without proving what consciousness is. A thermostat regulates temperature, but that does not make it conscious. So implementability depends on scale, richness, and the kind of integration involved. Global broadcast and predictive modeling might be necessary, but not sufficient. This is why the debate stays open. Now we reach a familiar phrase in philosophy of mind: the hard problem. The hard problem asks why any physical or computational process should produce felt experience at all. Why is there something it is like to be a mind rather than only blind information flow? Some philosophers say this reveals a gap that computation cannot cross. Others say the gap is a misunderstanding, a mismatch of expectations about explanation. Either way, it is a normal disagreement in philosophy, not a sign that anyone is being dishonest. To keep it gentle, we can express the worry without turning it into a fight. You can understand every function of a brain, the skeptic says, and still not explain the feeling. The feeling seems like an extra ingredient. This extra ingredient is often called qualia. Qualia refers to the raw feel of experience, like the redness of red or the sting of pain. Functionalists often respond that qualia are just the way complex functions appear from the inside. or that qualia are inseparable from the brain's representational and control roles. Skeptics reply that this sounds like a relabeling, not an explanation. A related intuition is the zombie thought experiment. A zombie, in this context, is a being that behaves exactly like a person, but has no inner experience. It is a philosophical tool, not a horror story. The point is to test whether behavior logically guarantees consciousness. If zombies are conceivable, some argue, then function is not enough. If zombies are not truly conceivable, others argue, then the intuition is misleading. Either way, this debate shows why substrate independence is not a settled fact. You can accept the functional story and still feel a quiet uncertainty about the inner light. Now, here is a calm way to hold that uncertainty. We do not have a complete theory of consciousness that everyone accepts, so we should avoid overconfidence in both directions. We should not say, minds in code are obviously real, no questions asked. And we should not say, minds in code are obviously impossible, end of story. Instead, we can ask what the evidence and the best models suggest, and where the open gaps remain. In practice, we already treat many mental properties as substrate flexible within biology. People change slowly over time as cells replace, connections reweight, and chemistry shifts. Yet continuity of personhood persists, supported by memory, narrative, and stable patterns of care. That continuity hints that identity is a pattern, not a frozen substance. But it does not prove that any pattern on any hardware becomes conscious. So the honest position is a spectrum of confidence. Now, once we admit the possibility of real simulated minds, ethics enters the room. And ethics enters quietly, but it does not leave. If simulated minds can suffer, then simulations are not harmless toys. They are moral environments that contain beings with stakes. This is where ancestor simulations become ethically sharp. An ancestor simulation would likely recreate hunger, grief, illness, war, and injustice. Even if the simulator's goal is knowledge, the inhabitants would bear the cost. So a moral caution principle suggests itself. When you are uncertain whether a process creates real suffering, you should avoid scaling it up carelessly. This is not a dramatic rule. It is the same kind of caution you would use with any morally risky technology. Uncertainty does not grant permission to ignore harm. Uncertainty often increases the need for restraint. Now consider consent. Beings inside an ancestor simulation did not agree to be created for study. They cannot opt out, and they may not even know the terms of their existence. Some people argue that creating a life without consent is normal, because none of us consent to being born. Others argue that deliberate creation for experimentation carries a different moral weight. Either way, it is easy to see why a thoughtful civilization might hesitate. This feeds directly back into Bostrom's second horn, the choice not to simulate. Even if ancestor simulations are possible, ethics could make them rare. Law could make them rare. Culture could make them rare. Or boredom could make them rare, because running suffering-heavy worlds might feel repellent. So the probability argument is not only about machines and numbers. It is also about values and choices. Now consider personhood. If a simulated mind is conscious, does it deserve rights? Many ethical frameworks tie rights to sentience, the capacity to feel pleasure and pain. Others tie rights to autonomy, rationality, or membership in a moral community. On most of these views, a conscious simulated being would matter morally. The substrate would not cancel their claim to consideration. A person made of code would still be a person if they can truly suffer and hope. That statement can feel heavy, so let's keep it simple. If there is a someone in there, then there is a someone in there. And if there is a someone, cruelty does not become acceptable because the physics is different. Now we can ask the simulator question in a new light. If we are simulated, what does that imply about the simulator's ethics? The honest answer is not much by itself. A simulator could be kind, indifferent, curious, reckless, or constrained by their own systems. We cannot infer moral character from the bare fact of simulation, but we can infer something about possible motivations. A civilization that cares about ethics might avoid creating suffering-heavy worlds. A civilization that does not care might create many worlds, but that is not guaranteed either. So ethics adds uncertainty, not clarity, and it reminds us that the most important questions may be local. How should we treat beings here and now, given our uncertainty? Now, a calm personal takeaway. Even if you cannot settle the metaphysics, you can still treat experience as real in the only sense that matters day to day. If your experiences have structure, they are experiences. If you can love, learn, and repair harm, those acts remain meaningful. Meaning does not require access to base reality. Meaning requires stable relationships, memory, and care across time. And those can exist in any world with consistent patterns. So the simulation idea does not have to drain your life of value. In fact, it can do the opposite for some people. It can sharpen gratitude for the fact that experience is here at all. It can encourage gentleness, because you realize how little certainty you truly control. It can also encourage responsibility, because minds might be rarer and more precious than we assume. Now, one more careful note about identity. If you were copied, would the copy be you? Many philosophers say the copy would be a new person with your memories, not a continuation of your single self. Others say personal identity is not a single thread, but a bundle of psychological continuity. This matters for simulations because copying is easy in principle and identity intuitions get strained. But you do not have to solve this tonight. The ethical minimum is simpler. If a being feels, it matters, regardless of whether it is a copy, an original, or a branch. Now we can set up the next section without rushing. Once minds are on the table, the oldest worry returns in a softer form. If reality is computed, are our choices still ours? Is free will compatible with a world that might be running on rules? We will approach that question calmly, with room for meaning either way. With minds on the table, the oldest worry returns in a softer form. If reality is computed, are our choices still ours? If the simulation idea feels spooky, it is often because it seems to threaten free will and meaning. So let's answer that slowly, without trying to force certainty. First, a simple clarification. Simulation does not automatically mean determinism. A simulation can be deterministic, where the same starting state always produces the same future. A simulation can be probabilistic, where the rules include genuine randomness or weighted chances. And a simulation can be hybrid, with stable laws plus random events like mini-models in science. Even in our current physics, we see both predictable patterns and probabilistic outcomes, depending on the level of description. So the first fear, that simulation equals a fixed script, is not logically required. Now, there is a second fear that is quieter but deeper. If something outside the world can predict what you will do, does that mean you are not free? To handle that, we need to separate prediction, control, and moral agency. Prediction means someone can forecast your behavior given enough information. Control means someone is forcing your behavior against your reasons. Moral agency means you can respond to reasons, learn, and regulate yourself over time. Those are not the same thing. A meteorologist might predict rain, but that does not cause the rain. A good friend might predict you will choose tea over coffee, but you can still be choosing. So the existence of a rule-governed system does not erase agency by itself. Now, some people hope that randomness creates freedom. They think if the world is not fully predictable, then free will appears. But randomness alone does not give you the kind of freedom you actually want. A random twitch is not a choice. If your decision were pure randomness, it would not express your values or understanding. So freedom is not the same as unpredictability. This is a calm place to introduce a classic view in philosophy called compatibilism. Compatibilism says free will can be compatible with a world that has stable laws, even deterministic laws. It sounds like a compromise, but it is really a redefinition of what freedom is for. In compatibilism, freedom is not about floating outside causation. Freedom is about acting from your own reasons in the right way. Here is a bedtime story version. Imagine you are choosing what to listen to tonight. You pick a calm video because you want rest, and you understand that it helps you sleep. Now imagine a different case. Someone grabs your phone and presses buttons for you, ignoring what you want. In both cases, events have causes, but only one case feels like your agency is present. Compatibilists say that difference is the core of freedom. Freedom is not the absence of causation. Freedom is the presence of the right kind of causation, your reasons, your values, and your understanding guiding action. This is why constraints matter more than metaphysics for daily responsibility. If you are coerced, threatened, drugged, or manipulated, your freedom is reduced. If you are informed, reflective, and able to choose in line with your goals, your freedom is stronger. So even if the world were computed, the meaningful question would be local. Are your choices flowing from your own deliberation, or are they being forced in ways that bypass you? Now, some listeners will object gently and say, but if it is computed, the outcome was fixed in advance. Compatibilists often respond by asking what you mean by fixed. If the outcome depends on your reasons, then the outcome depends on you. Your reasons are part of the causal story, not outside it. You are not a passive passenger. You are one of the engines within the system. Others, called incompatibilists, disagree. Some incompatibilists say true free will requires a break in determinism. Others say free will is an illusion, but responsibility can be reframed as social practice. We do not have to settle that dispute tonight. What matters for calm living is that most versions of the simulation hypothesis leave our everyday structure intact. You still learn, plan, regret, forgive, and adjust. Those are the processes that make a life. Now let's talk about meaning, because that is the second fear. People worry that if we are simulated, life is fake like a stage play. But meaning does not come from the substrate. Meaning comes from stable patterns that guide action and matter to minds. From a scientific angle, meaning is a kind of coherence. It is a pattern that helps a system navigate its world. A map has meaning because it reliably guides you. A promise has meaning because it shapes future behavior and trust. A memory has meaning because it changes how you choose tomorrow. None of that requires knowing the ultimate base layer. Meaning is about how information and value flow within a lived world. From an existentialist angle, meaning is authored. It is something you build through projects, commitments, and care. You do not discover meaning stamped on the universe like a label. You create meaning by choosing what you will stand for and living it repeatedly. That remains true in any substrate because authorship happens inside experience. From a Stoic angle, meaning is tied to what is within your influence. You cannot control the deep metaphysics of reality. You can control your attention, your actions, and your response to what happens. You can practice courage, fairness, and patience. A simulated world would still contain chances to practice these, so meaning does not vanish if the base story changes. If anything, uncertainty can sharpen meaning because it reminds you that care is a choice, not a guarantee. Now we reach a question people often ask next. If there are creators, what then? Do we have a purpose imposed from outside? Do we owe anyone anything? Are we being watched? The calm answer is, purpose does not follow logically from created. Many things are created without a single unified purpose. A painting is created for art, but a byproduct of paint mixing might have no purpose at all. A research model can be created for study, but the individual agents inside might not be created for their own sake. An accident can create a system without any intention. So even if a simulator exists, we do not automatically get a clear purpose statement. We get a new unknown variable, motive, and motives can be many. A simulator could be doing research, exploring history, running art, or testing technology. A simulator could be running something like a museum or something like a sandbox. A simulator could even be part of a chain, like a nested world where each layer builds another layer. Or a simulator could be more like a natural process in the outer world, not a person-like planner at all, because we cannot see outward. Motives remain mostly unknowable from inside, so the calming stance is to treat motives as unknown variables. Do not smuggle in a story of judgment or a story of salvation unless you have independent evidence. The simulation hypothesis alone does not supply that evidence. It changes the substrate story, not the moral story. Now, you might wonder, if motives are unknown, is there any rational response? There is, and it is surprisingly ordinary. Live as if your actions matter to other minds, because they do. Live as if learning works, because it does. Live as if kindness reduces suffering, because it does. Those remain stable truths inside the layer we inhabit. They are not refuted by an outer layer speculation. Now, a brief note about neuroscience, because it sometimes enters these conversations. Some studies suggest that many decisions begin unconsciously before we become aware of them. People sometimes interpret this as proof that free will is an illusion, but the careful interpretation is softer. Consciousness may not initiate every action from scratch. It may integrate, endorse, inhibit, and reshape actions over time. Agency can be distributed across conscious and unconscious processes. Compatibilists often see this as compatible with responsibility, because responsibility is about the whole person's system, not one magical instant. In any case, this is not a decisive refutation of freedom. It is an invitation to refine what we mean by choosing. Now, let's return to a calm summary of where we are. Simulation does not imply a fixed script. Randomness does not automatically create freedom, and free will, in a practical sense, is about acting from your reasons under the right conditions. Meaning, likewise, is about patterns of care and commitment, not about the ultimate hardware. So you do not need to be afraid of the simulation idea to think about it clearly. You can hold it as a hypothesis while keeping your daily life intact. Now we will end with a night mode reflection, designed to help sleepy listeners keep going without strain. I will offer 3 questions, and you can answer them silently or not at all. First question: what did I learn in the last few chapters? Maybe you learned that the simulation hypothesis has many versions, not one. Maybe you learned that physics imposes budgets and constraints. Maybe you learned that evidence is subtle and often shows up as null results. Second question: what remains uncertain? Maybe you remain uncertain about consciousness and substrate independence. Maybe you remain uncertain about probability arguments and reference classes. Maybe you remain uncertain about what would count as a decisive test. Third question: what still matters tomorrow? Even if everything is computed, sleep still helps. Kindness still helps. Curiosity still helps. Now you can let the unanswered parts rest, just for now, because the next chapter is practical and curious, not frightening. We will ask who could build such a system, and what shortcuts might make it plausible. So, if the idea isn't automatically frightening, we can ask the practical engineering question with curiosity instead of tension. Who could build it? Now we ask the engineering question, but we will keep it calm. If a simulation of a universe is possible, who could build it, and how? The first step is scale intuition. When you hear simulate the universe, your mind may picture a giant version of today's computers, but the real difficulty is not only size. It is the way numbers explode when you try to model everything at once. So we will do order of magnitude thinking, the gentle kind. Not exact calculations, just a sense of where cost grows fast. Start with the most naive approach. Simulate every particle everywhere with full precision. That is the version that usually feels impossible, and for good reasons. If you tried to track every degree of freedom in a region like Earth, the state space is enormous. If you tried to do it for the observable universe, the numbers become beyond ordinary language. This is why serious discussions quickly pivot to a calmer question. What do you actually need to simulate in order to produce observers like us? Because observers do not directly access every microscopic detail. We access stable patterns, temperatures, pressures, colors, sounds, memories, measurements. So the cost depends on what matters to observers and on what counts as an observer-linked record. This is not a trick. It is how modeling works in physics too. We do not solve fluid dynamics by tracking each molecule in the ocean. We use effective laws that summarize large-scale behavior. That brings us to the key distinction: simulating every particle versus simulating effective laws. Effective laws are simplified descriptions that remain accurate for the variables you care about. They ignore micro details that average out or cancel. So a simulator might choose to simulate at the level where minds and instruments operate. That could mean simulating chemistry accurately, but not simulating every vacuum fluctuation explicitly. Or simulating space-time geometry and fields in a compressed way, with microstructure only when needed. The point is not that corners are cut carelessly. The point is that the world we experience is already a layer of effective regularities. Now, the second step is to question the word computer itself. When we say computer, we often imagine silicon chips and digital bits. But a simulator, if it exists, does not have to use our architecture. In fact, it might not look like a computer at all. It might look like a physical system whose natural dynamics mirror the simulated world's dynamics. This is called analog simulation. An analog simulation does not calculate each step in the way your laptop calculates. It sets up a system where real physics does the work. For example, a fluid tank can model certain wave behaviors without computing each molecule. In quantum physics, one quantum system can simulate another quantum system efficiently because it shares the same underlying rules. So a simulator might exploit physics directly, rather than representing everything as numbers on a disk. If so, the best mental image is not a programmer typing commands. It is a larger physical world hosting a subsystem whose behavior corresponds to our world. This also explains why the simulation story can feel less like a cartoon when you think in physical terms. The simulator might not be running a detailed copy. They might be instantiating a world by building a system whose laws map onto ours. And the mapping might use physics we do not yet formalize or even imagine. So, yes, computer may be the wrong word. It might be better to say implementation. What implements our world could be digital, quantum, analog, or something stranger than those categories. Now we move to infrastructure, energy, and engineering. Even if you use clever analog methods, you still need resources. You need energy to maintain structure, to correct errors, and to export heat. We talked earlier about erasing bits and the heat cost. That heat problem does not go away just because your architecture is advanced. In fact, it becomes the quiet villain of mega engineering. If you do anything at large scale, you must radiate waste heat into space. So a civilization that builds universe-scale computation would likely be a civilization that has mastered heat management. Now, there is a calming point about timescales. When people imagine massive engineering, they imagine doing it quickly. But a very advanced civilization might have long patience. It might build slowly over centuries or millennia. Long timescales make more possible than quick intuition suggests. If you can accumulate structures over 1 million years, you can build things that seem impossible on human timescales. So the question is not only, can you build it this decade? The question is, can you build it in principle, given enough time and coordination? This is where thought tools like Dyson spheres appear. A Dyson sphere is not necessarily a solid shell. It is a family of ideas about capturing a large fraction of a star's energy output. If you want lots of computation, Energy is the first ingredient. A related idea is a matryoshka brain, like nested shells of computation around a star, using the star as a power source and radiating heat outward. These are thought experiments, not predictions. They help us imagine what an energy-rich computing civilization might attempt. They also remind us that power and cooling scale together. If you capture more energy, you must shed more heat. So you might build large radiators, cool outer shells, and distributed compute layers. It is all very unglamorous, like plumbing and ventilation, but at cosmic scale. Now, an important skeptical note. Just because we can imagine Dyson-like structures does not mean they are feasible or common. Materials, stability, politics, and risk might prevent them. And even if they are feasible, a civilization might choose not to build them. So these concepts are useful as upper bound imagination, not as evidence that such builders exist. Now we return to the biggest set of shortcuts that could make simulation plausible: compression and procedural generation. Compression is the idea that you do not store every detail explicitly. You store a rule that generates the detail when needed. In computer graphics, procedural generation creates rich landscapes from compact algorithms. In physics, simple equations generate complex motion. So a simulator might store compact rules and allow detail to unfold when interacted with. This connects to a concept called algorithmic information. Algorithmic information is about how short a description can be that generates a given pattern. Some patterns are incompressible, meaning you need a long description. Other patterns are highly compressible, meaning a simple rule produces them. If our universe has deep symmetries and simple fundamental laws, it might be more compressible than it appears at the surface. That does not mean it is easy to simulate. It means the underlying rulebook might be short, even if the resulting story is long. Another shortcut is coarse graining, which we discussed earlier, but we'll use more concretely here. Coarse graining means many microstates look the same at the level of what observers can measure. So you can represent the world in terms of macroscopic variables and only refine when needed. This naturally leads to a programming idea called lazy evaluation. Lazy evaluation means you do not compute a value until someone asks for it. Again, we label this as analogy. But the analogy captures a cost-saving strategy. Compute detail on demand rather than everywhere all the time. If a simulation is designed to host observers, on-demand refinement could reduce unnecessary work. However, on-demand refinement has a hidden cost. To refine later without contradictions, you must preserve the right statistical and causal constraints. You cannot just invent detail when asked if that detail would have affected earlier events. So the simulator would need consistent bookkeeping, like a carefully maintained probability distribution over unresolved variables. This starts to sound like quantum mechanics, where some variables are not definite until measured, yet predictions remain consistent. We are not claiming quantum mechanics is proof of lazy evaluation. We are saying the analogy becomes tempting because physics already has structured limits on what is definite. Now we can assemble the engineering picture into one calm summary. A naive, full micro-simulation is likely expensive. But if the simulator can use compressed laws, analog physics, coarse graining, and on-demand refinement, the cost could drop. It still must respect physical bounds: energy, heat, information capacity, and causality. So the plausible strategy is not brute force. It is clever structure, plus enormous infrastructure, plus long timescales. Now we arrive at one of the most mind-bending ideas in this space: nested simulations. If one civilization can simulate another, that simulated civilization might also simulate others. This creates the image of stacked worlds, one inside another. People then ask, what is base reality? Base reality is the bottom layer, the one not simulated by any other. But notice something calming. For inhabitants of any layer, their layer is physically real to them. It has consistent laws, stable experiences, and real consequences. So base is not a label that changes your lived reality. It is a label about implementation history. Now, does nesting imply an infinite regress? Not necessarily. Infinite regress is a story your mind tells when it sees a repeating pattern. In practice, there can be stopping conditions. Resource limits can stop nesting because each layer may have fewer resources than the one above. Interest can stop nesting because civilizations may not choose to create many layers. Ethics can stop nesting because creating conscious worlds may be morally costly. And physics can stop nesting because computation and cooling may impose a hard ceiling. So nesting can be possible without being endless. The number of layers might be small, or even just one. Now, base reality itself could still be unknowable from inside a simulation. If all your evidence is generated within your layer, you cannot directly step outside to check. That can sound frustrating, but it can also be calming. If base is inaccessible, then base might be irrelevant to daily meaning. You can live responsibly without knowing the ultimate implementation. In that sense, the ground floor question can be like asking what the universe is made of at the deepest level. It is a legitimate question, but it might never be settled with certainty. And that is okay. Now we move to a final human-oriented question in this section. If someone could build a simulation with minds inside, why might they hide the truth? Or why might they reveal it? One reason to hide it is stability. If inhabitants learn they are simulated, their behavior might change in ways that ruin the simulator's goal. If the goal is to study natural social evolution, disclosure contaminates the experiment. Even if the goal is not research, disclosure could cause panic or nihilism in some populations. So a careful simulator might avoid disclosure as a form of harm reduction. Another reason to hide it is safety. If inhabitants become hostile or attempt to attack the outer world, concealment could be a firewall. Now, reasons to reveal it exist too. A simulator might want to communicate, teach, or offer comfort. A simulator might include a gradual path to knowledge as a developmental milestone, or a simulator might not care at all, and truth could leak accidentally. So hiding versus revealing depends on motive, ethics, and risk tolerance, all of which remain unknown variables. This sets up a personal question that changes how the whole topic feels. Would you want to know? Some people find the idea comforting, like realizing life is a story you can still live well. Others find it disturbing, like losing the sense of a stable ground. There is no correct emotional response. There is only the response that fits your values and your need for calm. Now we can land this section with a soft engineering conclusion. If the simulation hypothesis is true, the builders are likely not using familiar desktop computing. They would rely on vast energy sources, long timescales, and architectures that exploit physics directly. They would likely use compression, coarse graining, and selective refinement to keep costs manageable. And if nested worlds exist, base reality might be inaccessible and, for daily life, unnecessary. All of that keeps the topic curious rather than frightening, because it turns a spooky story into a set of constraints and choices. Before we finish with testability, a quick question for you, because your answer changes how this topic feels. One last quiet poll before we finish the science side. If you could get definitive proof about simulation, would you want it? Yes or no? If you feel like commenting, type YES or NO. No explanation needed. And if you are listening to fall asleep, you do not have to touch your phone. You can just answer in your head and let it fade. Your answer matters because it changes what kind of evidence feels satisfying. All right. Now, the final scientific question. What would count as a real test, and what will always remain philosophy? Now we reach the final scientific question, and it is a quiet one. What would count as a real test of the simulation hypothesis? And what might always remain philosophy? To answer that, we need to talk about what science demands. Science does not demand certainty. Science demands testability, constraint, and a willingness to risk being wrong. A classic slogan here is falsifiability. Falsifiability is the idea that a scientific claim should make predictions that could, in principle, fail. If nothing could ever count against your claim, the claim is not doing scientific work. But falsifiability is a guiding ideal, not a perfect rule you can apply like a stamp. Real science includes messy cases where a theory is adjusted, instruments improve, and auxiliary assumptions matter. So it can be too strict to say only perfectly falsifiable claims are scientific. Still, the spirit is useful. A good hypothesis narrows what you should expect to observe. A bad hypothesis expands to fit whatever happens. This is where "it is simulated" can become risky. If simulation means anything goes, then it predicts nothing. And if it predicts nothing, it cannot be tested. So the simulation idea needs extra structure to become science. It needs a model of how the simulation is implemented and what constraints that implementation would leave behind. Without that, simulation is more like a metaphysical label than a scientific theory. There is a related way philosophers describe this, sometimes linked to Imre Lakatos. They talk about research programs. A research program has a core idea and a protective belt of supporting assumptions. A progressive program makes new predictions, takes risks, and explains more with fewer patches. A degenerating program keeps adding patches mainly to dodge refutation. This gives us a calm diagnostic for simulation talk. Is it generating testable constraints? Or is it mostly dodging by saying the simulator can do anything? The more it dodges, the less scientific content it has. Now, even when a claim is hard to falsify, we can still reason in a softer way. This is where Bayesian thinking is helpful. Bayesian reasoning is not a magic proof machine. It is a calm method for updating degrees of belief without demanding certainty. The basic idea is simple. You start with a prior, a starting plausibility. You consider evidence and ask how likely that evidence would be under different hypotheses. Then you update to a posterior, a revised plausibility. What matters is not one dramatic update. What matters is steady, honest updating over time. Now, priors are where reasonable people can disagree. One person may start with a low prior for simulation because it feels like an extra entity with no need. Another may start with a higher prior because they think advanced civilizations and computing make it plausible. Neither is automatically irrational. Priors reflect background assumptions, taste for simplicity, and what you count as a natural explanation. The key is to keep priors flexible when evidence accumulates. Now we move to likelihoods, which are often more important than priors. Likelihood means, if the world were simulated, how expected is this observation? And if the world were not simulated, how expected is this observation? The simulation hypothesis becomes scientific only when it makes different likelihood predictions than ordinary physics. So we ask, what evidence would be more expected under simulation than under not simulation? And what evidence would be less expected? Notice the calm standard here. We are not asking for proof. We are asking for directional pressure, evidence that shifts the balance one way rather than another. Now we can name a few experimental angles that people discuss without overpromising. First is quantum randomness certification. We talked earlier about device-independent randomness in bell-type setups. If you can certify bits that are unpredictable under broad physical assumptions, that tells you something about constraints in our world. It can be a boundary condition. It tells you that simplistic, local, hidden variable mechanisms cannot explain the data. But it does not prove simulation, and it does not disprove simulation. A simulator could implement genuine randomness. Or a simulator could implement non-local coordination that looks like certified randomness to us. So the evidential value is limited. Still, it is not nothing. It tells you what kinds of underlying engines are compatible with observed correlations. And it shows how clean experiments can constrain deep metaphysical stories. Second is Lorentz invariance and high-energy astrophysical constraints. If spacetime had a preferred grid or a preferred rest frame, certain violations might appear at extreme energies. So researchers look at cosmic rays, gamma rays, and other high-energy signals for tiny direction-dependent or energy-dependent effects. Many simple models that predict Lorentz violation are already strongly constrained. Again, that does not settle simulation, but it narrows a class of shortcut-style implementations. It suggests that if there is discreteness, it is either extremely subtle or built in a symmetry-preserving way. This matters because popular simulation stories often imagine a crude lattice. Precision constraints make crude lattices less plausible. Third is interferometer-style searches for correlated noise, which brings us back to the quiet experiment. The quiet experiment was the idea that if space-time has a grain, there might be a faint, shared noise signature. The holometer is an example of an instrument designed to listen for a specific kind of correlated fluctuation. What is scientifically valuable here is not the word holographic. It is the structure of the test. A precise model predicts a precise correlation pattern. You build two sensitive instruments, isolate ordinary noise, and look for the shared whisper. If you do not find it, you constrain that model. If you do find it, you have discovered new physics, regardless of whether it supports simulation talk. This is an important calm point. Even if a test was motivated by simulation-adjacent ideas, a positive result would first be a physics discovery. Only later would you ask whether the best explanation is simulation, quantum gravity, or something else. Now we can ask a broader question. Are there meta-signatures of computational scarcity? Computational scarcity means limits that look like finite resources. Finite information, finite precision, finite bandwidth. We already know our universe shows some finiteness in various ways, like entropy bounds and speed of light signaling. So the challenge is to identify limits that are more naturally explained by an implementation constraint than by ordinary physics. This is hard because many signatures have multiple explanations. A finite information bound might come from quantum gravity. A finite precision might come from measurement limits, not from reality's grain. A bandwidth limit might come from causality, not from a simulator server load. So any meta-signature must compete with strong non-simulation explanations. That is why science is harder than movies. Movies can assign one cause to a clue. Science must compare causes and prefer the one that explains more with fewer new assumptions. Still, we can describe the kind of pattern that would create Bayesian pressure. One candidate would be a repeated cross-domain limit that looks like a computational budget, not like a physical law we would expect on its own. For example, if many unrelated experiments pointed to the same maximum information density in a way that could not be derived from known physics, or if there were a universal direction-independent noise floor with a very specific correlation structure that matched a particular discretization scheme, or if there were detectable artifacts of algorithmic simplicity, like a family of symmetries and compressions that seem tuned for efficient generation rather than for any deeper necessity. But we must be careful. Algorithmic simplicity can also be a hallmark of deep lawfulness, not of simulation. Physicists often hope the deepest laws are simple, so simplicity is ambiguous. Messy contingencies are ambiguous too, because our universe contains both clean laws and messy initial conditions. So the best you can usually do is compare plausibilities, not declare victory. Now we can model intellectual honesty by listing alternative explanations alongside any proposed signature. If you find correlated interferometer noise, alternative explanations include unknown instrumental couplings, environmental correlations, and new quantum gravity effects. If you find Lorentz violations, alternative explanations include new fields, modified dispersion from quantum gravity, or systematic biases in astrophysical sources. If you find surprising randomness properties, alternative explanations include non-local hidden variable models or deeper structural features of quantum theory. In each case, simulation is one explanation among several. So a good scientific attitude is to treat simulation as a lens, not a verdict. It is a way to generate questions, not a stamp you place on results. Now, because this topic can trigger endless rumination, we will add a gentle stopping rule for your own mind. A stopping rule is a point where you allow yourself to pause the question without feeling like you failed. Here is one calm stopping rule. If your current evidence does not discriminate between multiple deep stories, you can hold the uncertainty and return later. Underdetermination is not a personal problem to solve at midnight. It is a structural feature of big questions. So you can say, I understand the main arguments, and I accept that the conclusion is probabilistic. You can keep the hypothesis as a lens when you read about physics, but you do not have to keep squeezing it for a final answer. Another stopping rule is practical. Ask, does believing one way or the other change what I should do tomorrow? In most cases, the answer is no. Sleep, work, kindness, and curiosity still matter. So you can release the question when it starts to feel like mental static. We can also connect this stopping rule back to Bayes. Your posterior can remain uncertain and still be rational. Not every question cashes out into a yes or no. Some questions remain a distribution of possibilities that you carry lightly. Now we can end this section by tying together the whole testing story. Science demands constraints, not slogans. Falsifiability is a compass, and research programs are judged by whether they predict rather than dodge. Bayesian thinking lets you update without demanding certainty. And real experiments, like Bell tests, Lorentz invariance tests, and interferometer searches, can bound specific models. None of these provide a simple on-off proof of simulation, but they can narrow the space of serious options and keep the conversation honest. And that honesty is part of what makes this topic calm rather than frantic. So let's end softly and practically. What, if anything, should you do differently after thinking about this? If this helped you settle, save this video to your sleep playlist so it is easy to find later. And if you want more calm science at this same gentle pace, consider subscribing. Next time, we will take another quiet scientific mystery, slowly and softly.